Thanks everyone for attending the talk. And by the way, Joseph, I liked a lot your talk, so keep it up because I like a lot the way you present these things. Anyway, so in this talk we're going to talk about Chebyshev tensors and machine learning, and in particular we're going to talk about them in a more kind of theoretical basis to understand what we're trying to do. And after that, we're going to go to one example, which is how to simulate sensitivities dynamically in a simulation. We chose sensitivities because it is the most difficult thing to simulate right now. And in order to see what I think is the strength of this technique, we thought that sensitivities was ideal. And of course, with that, we're going to show how we can simulate dynamic initial margin. And also at the end, we'll talk a little bit about the CCR like CBA or XVAs in general or IMM capital simulations, and also a bit about FRTB. This talk is given by my friend Mariano Zeron and about myself, Ignacio. Okay. So first of all, as a quick introduction, sometimes when we are in a conference, etc., we are asked who we are, Mocax Intelligence, and basically what I always say is that a bit of a joking, we say we are a bunch of nerds who we believe that sometimes when we face a calculation that seems to be impossible, we believe that if we put the right mindset, effort, intelligence, and patience to a great extent to it, what seems to be impossible becomes doable. And in fact, we have experienced that a few times in our lives, and we feel highly motivated by this type of impossible computation. So if what I just said resonates with you, get in touch with us because we love collaborations. So in terms of what we're going to cover in this talk, first of all, we are going to talk about the pricing problem in risk calculations, a very brief introduction so that we are on the same page, because I think most of us are aware of this problem. That's why we are here, I guess. But just so that we're on the same page, we'll talk about it a little bit. After that, we are going to introduce Chebyshev tensors and how to apply them to risk engines. We're going to see their strengths, and also we're going to talk about the limitation that it has. And then we are going to introduce the extension algorithm. And in fact, it was yesterday introduced as well by Catherine Glau in a very good talk that she gave. And we are going to see how combining both tools, we can create a fairly strong way to create to accelerate risk calculations. And then once this is established, we will use the dynamic sensitivities, dynamic initial margin as an example, and then of course a bit of as well as CCR and IMA FRTB as well. Just as a couple of things before we start with the crux of the presentation. Right this past weekend, we have created a YouTube channel. I'm very excited about it. So it is a YouTube channel in which we basically want to share videos that we have about all these things that we're going to discuss today. And so if you like what we say here, go to YouTube, just type in the box Mocax, and our channel will pop up. And then, of course, if you like what we say, the kind of content that we have, subscribe to it, and we will keep in touch. Also, we are very happy and proud to say that we were rated as a top 3 fintech startup in risk analytics fairly recently. And also, just as a little note, just to know that the application of some of the techniques that we're presenting here are covered by a patent, but that should not be a problem for anyone because the patent holders are happy for anyone in the world to use these methods and these techniques. So if you're interested in some sort of a license or something like that, just get in touch with us and we will give you all the information that you need. All right. So let's go now into the crux of the presentation, which is, let's start introducing the problem that we want to tackle, which is the pricing problem in risk calculations. So in a nutshell, in a risk engine, usually you have these steps, more or less. First of all, you have to prepare the engine, of course. Then you have to generate a number of scenarios, typically a high number of scenarios, market scenarios. And then in each of these scenarios, we want to price a portfolio. And then from all these prices, we are going to get some statistics, some averages, some percentiles. And from that, it's going to give us what I call the risk metrics and profiles sometimes. These are the risk metrics that usually the engine, the risk engine is going to push into downstream systems, right? So the problem from all this, from the computational point of view, tends to be in the reevaluation step. That, for example, in the case of XVA, we typically have 10,000 scenarios, 100 time steps, which means we need to do 1 million reevaluations of the whole portfolio in each run. Of course, if you have sensitivities, either bump reval or AAD, you're adding more complexity to the problem. Similar type of problem we have with IMM Capital. In the new version of FRTB, that is keeps on being delayed, but it's going to come sooner or later. It's going to come. It's going to be with us. Also, we need a few thousand reevaluations in each run. And in general, all this is a computational problem. So the alternative is basically, can we create a fast version, a proxy for the function, for the pricing function that we can use instead of the original function that is very slow and heavy to compute? And the question is, if we are able to do that, the point is that this needs to be fast, first of all. Secondly, accurate, of course. There needs to be a level of accuracy. And ideally, we want to not only make it accurate, but we want to control the accuracy. Also, it needs to be easy to calibrate. Also, it needs to be stable. The last thing that we want is that we have a proxy pricer that it stops working in the middle of a crisis. So it needs to be stable under nearly all market conditions. It needs to be low in memory use, and it needs to be able to be computed on a cloud-based grid. So it needs to be parallelizable. So this is the goal that we have. We want to be able to create a proxy function for a pricer with all these characteristics, all these characteristics. So basically, there are lots of attempts in the literature in the past, and usually I try to see this into two types of family. We have a random sampling type of approach and deterministic sampling approach. The simple, for example, the old ones are one that has been around for around 10 years or more. For random sampling is least square or linear regression, in which basically we are estimating the value of the function in a number of points, and then we are trying to fit a polynomial through them. This method was really strong around 10 years ago. And then another one that is really, really strong and well known is, of course, the standard linear or spline interpolation methods, local coordinate coding, for example, as well. That is very popular as well. Actually, it's less popular, but it was a good attempt. That's what I was trying to say. It was a good attempt to solve this problem. And basically, what they do is you have a fixed points, typically equidistant, if we know nothing about the function, and then we call the function those points, and then we interpolate in between. So these two approaches are very straightforward, very well known, and of course, it has some strong limitations. Hence, we are here, I guess. Then lately, of course, we had right before the talk by Joseph, a very good talk, in which he explained deep neural networks, in which we are basically going to sample the function, and then we are going to pass the function through a neural network. I'm going to calibrate it to minimize an error given all these data points. And then a final version of all these four options is deterministic sampling with sophisticated methods. Is what I personally like calling smart sampling, in which when we sample the function that we want to approximate, instead of doing naively in for example, a equidistant point, we're going to choose some very specific points that unleash some mathematical properties that are going to be very relevant to us. So in this talk, what we're going to do is we're going to do a combination of the two at the bottom. We're going to start talking about one of the, arguably maybe the best or one of the best methods for smart sampling, which is the Chebyshev method, Chebyshev tensors. Once we understand that, we're going to see how it can work very well in some contexts, but it has some limitations. And then we are going to borrow some ideas from deep neural networks in order to optimize it. And then once we have this, we're going to show with a few examples how we can solve problems that seems impossible at the beginning of the conversation maybe 5 years ago they were thought to be impossible. So I think this is the introduction, and now I'm going to pass the baton to Mariano, who gives the presentation very well.
Thank you very much. So I'm going to share my screen now. Please let me know when you when you see it.
We see your PowerPoint, yeah.
Yep. And we're here, right? Good. So yeah, thank you very much. So Ignacio presented to us what the main problem is that we're going to be focusing on, which is the pricing problem in risk calculations. And now we're going to talk about one of the main objects that we're going to be using in order to solve this problem, which are Chebyshev tensors. I'm going to talk about some of the mathematics behind Chebyshev tensors. I'm going to start very, very simple and then try and quickly get to the main results, which are relevant for the applications that we're going to be presenting later on. So first of all, what's a tensor? And a tensor is just simply a collection of points in Euclidean space with values associated to them. So this is a perfect example in 3 dimensions, but it can be in any dimension. Associated to a tensor, we always consider polynomial interpolants. In fact, we're going to consider them to be equivalent objects for the following reason. Take, for example, a one-dimensional tensor. So it's just a grid of points in one dimension. Somehow you've got values on those points that gives you a tensor. And what we know is that there is a unique polynomial that goes through these values. And this unique polynomial is going to be the polynomial interpolant that we associate to the tensor. And why do we use these tensors and corresponding polynomial interpolants? Because we want to approximate functions. And how do we do that? Well, consider this simple example, a one-dimensional function that you've got below here. Consider any grid of points on its domain, doesn't matter how they're distributed in principle. Then we need, in order to define a tensor, values on those points. Given that we want to approximate a function, just evaluate the function on those points. And this is going to be, by the way, an important thing, the way that we go from the function to a tensor. So we evaluate the function on that grid of points, we obtain the tensor, and we had already said that we've got a corresponding polynomial interpolant. And we use that polynomial interpolant as a proxy for the function. The question, of course, is whether that proxy is good or not, right? And the name of the game is going to be increase the number of grid points, which defines a sequence of interpolants or polynomials. And hopefully we get that sequence of polynomials gets closer and closer to the function. Unfortunately, that doesn't always happen. And that's part of the reason why, for a good part of the 20th century, polynomial interpolation enjoyed a bad reputation. In particular, there are 2 problems that stand out. One of them was obtained at the beginning of the 20th century, in 1901, by Runge. He came up with a function that nowadays is known as a Runge function, a very well-behaved function, analytic, so high degrees of smoothness. And what he proved is that if you've got equidistant grids, this sequence of tensors, or equivalently polynomials, actually diverge away from the function, which is the opposite behavior to the one that he would like to have. Roughly at the same time, Faber proved that for the whole class of continuous functions, there's no interpolation scheme that works for this class. So at least on the face of it, it seemed that polynomial interpolation was not the right way of approximating functions if what you're interested in is using polynomials. However, something that was missed for a good part of the 20th century is that by adjusting a couple of things, then the properties completely change. The first of those things is the geometry of the points, and that is given by the Chebyshev points. This is the right geometry to work with. On the left-hand side, here below, you see the analytic definition of Chebyshev points. Very simple to implement, of course. On the right-hand side, you see the geometric sort of version of it. In one dimension, of course, this can be extended to higher dimensions. Take the interval -1 to 1, the upper half of the unitary circle, take equidistant points on that unitary circle, and then project them down. Naturally, just by the way that they're defined, they're going to be agglomerating towards the endpoints. And these are the Chebyshev points. Now, the second condition that we need to impose in order to be able to work with these kind of tensors distributed according to Chebyshev is we need to restrict ourselves to a smaller class of functions, not just continuous functions, but slightly smaller. And in fact, we start getting very good results by simply demanding the function to be Lipschitz continuous, which is a mild restriction on the function. Now, the following theorem is stated for analytic functions, of which the Runge function is an example. And the reason why we restrict ourselves to analytic functions is because for the applications we're interested in, this is good enough. And not only good enough, but it gives very, very, very good results. This theorem that you see on screen It's actually a combination of results, some of which were proved at the beginning of the 20th century, some of them much more recent in the 21st century. And it says that if f is an analytic function, doesn't matter what the dimension is, then as you increase the number of grid points on the Chebyshev tensor, then the sequence of polynomial interpolants that you define with the tensors converges quasi-exponentially to the function as this grid increases in size. Now, why is this important for us? Well, it means, given that it's exponential with respect to the n, and n is the number of grid points, it means that the number of times that you have to evaluate the function to generate the corresponding tensor doesn't need to be that high for the degree of accuracy to be very high. And this is going to have huge implications for the applications, that we're interested in. So, so at the beginning we said, okay, fine, not all tensors work, equidistant points. On the Runge function, terrible results, but we changed that for Chebyshev points, and the situation completely changes. What's going on here? And one way of looking at it comes from potential theory. And we start with this formula, which is one of the most important formulas in function approximation, called the Hermit integral formula. And it basically captures the error of approximation of P, the interpolant, with respect to f, the function that we want to approximate, in terms of an integral. But what's important is what's inside the integral. Inside the integral, we've got an expression of the potential field associated to a collection of charges in space. So think of the charges in space as being the grid points of the tensor. So in the case of a one-dimensional example, very simple, you would have on the real line here, you have these points over which you're going to be interpolating, which are, let's say, your charges in space. These charges have a field. Of course, you see the field in 2 dimensions on the complex plane. And of course, as you change the distribution of the charges, this field will change. And the energy associated to that field changes. But it so happens that the energy of that field is directly related to this integral. So by changing the distribution of points, you'll change the value of the integral and hence the error of approximation. And it so happens that if you've got equidistant points, for example, the energy of the field generated tends to be high. And in some cases, like for the Runge function, this difference, as you increase the number of charges in the system, actually explodes. Whereas if you change the distribution to Chebyshev, you achieve a minimal state of energy, which actually gives you, as a result, that this difference decreases exponentially as you increase the number of charges in the system. So it's a bit of a subtle difference between the two, but enough so that in some cases you get divergence when equidistant, you correct it with Chebyshev points, and you get very good rates of convergence.
I have to say that when being a physicist by education, I started to get more deeper and deeper into all this Chebyshev approximation theory, and for me it was a bit of magic. And then when I saw this, when I understood this, it all came to light and it all kind of started to shine, because everything, all the problems that as a physicist when I was a student, you know, the typical problems of you have X charges in this space, compute the state of minimal energy. Well, that is exactly what we are doing here. When we are trying to find the problem of trying to find the distribution, the geometry of the points in which to interpolate is the same as the problem of minimizing the energy of the potential that is shown in the screen. And personally, I find it fascinating.
Good. So this is just sort of a way of looking into how or why Chebyshev points are pretty good when it comes to these kind of problems. So just to see it in practice in the functions that we're interested in, we carried out the following test. So take the Black-Scholes pricing function in 2 dimensions. So we varied spot and vol, right? So it's a surface that we want to approximate using tensors. And we considered 2 types of tensors, equidistant grids and Chebyshev grids. And what we did is consider a collection of grids, and for each of them computed the error empirically, directly comparing it to the Black-Scholes pricing function. And the results are what you see on the right-hand side. On the x-axis, we've got the number of grid points of the tensor. And on the y-axis, we've got the error of approximation. In log scale, it's very important because we know that the convergence of Chebyshev grids is exponential. So you need to change it to log scale so that you can see it. And these are the results that we obtained. The red curve is the one corresponding to Chebyshev grid. So the Chebyshev grid, which of course decays the way that you would expect. The equidistant grid, on the other hand, even though it improves in terms of accuracy as you increase the number of grid points, it doesn't decay at the same rate. And if you take a look at, for example, here, the grids with 250 points, the error for the Chebyshev grid is 10 to the minus 7, whereas for the other one is 10 to the minus 1. The difference is huge. Even the error of 10 to the minus 1, which the equidistant grid achieves with 250 points, would have been achieved with about 15 using the Chebyshev grid. So the difference is pretty big, and only through the change of the distribution of the grid, which is the important aspect to highlight. Good. So far we've spoken about these Chebyshev tensors. They have really good convergence properties. But another important aspect is that we should always bear in mind is how am I going to evaluate these objects, given that we're interested in working with real problems on a computer. It's very important to always bear in mind that some of the algorithms out there that work very well on paper, they don't necessarily translate into good results when you implement them on a computer, because the rounding off errors in computers can accumulate to the point that then you obtain completely rubbish results. So it's always very important to work with numerically stable algorithms, and the right algorithm or formula to work with when it comes to Chebyshev tensors is the barycentric interpolation formula. This formula, as you can see in the middle of the screen, this is for the one-dimensional case, can be extended to higher dimensions, has three important properties to highlight. The first one, as I said, is that it's numerically stable. The second is that it's linear. It evaluates in linear time with respect to the n. Remember that n is the number of grid points on your tensor, or equivalently, the number of times that you evaluate the function to obtain the tensor. This speed of evaluation combines really well with the convergence properties that we mentioned before, because the exponential convergence says that n doesn't need to be that high for the accuracy to be high. Here, we know the tensor is going to have a low n, but we, on top of that, know that the barycentric interpolation formula evaluates in linear time with respect to that small n. So both of them combine really, really well. And the third one is, if you look at the formula only involves Chebyshev points and the values of a function of Chebyshev points. So only the information at the level of the tensor. You don't need to go from tensor to polynomial interpolant to then evaluate. You can evaluate directly from the tensor. This is a unique property of these Chebyshev tensors. So now we've got the tensor, how to evaluate it. But there are a couple of more properties that we would like to highlight, which are quite useful in a lot of settings. The first of them have to do with the estimation of the error as an approximating objects that Chebyshev tensors are. And this says the following thing. Before we saw that the barycentric interpolation formula only uses the information at the level of the tensor. But using those values, the values of the function on Chebyshev points, you can apply to them the fast Fourier transform to obtain this expression for the interpolant. And that expression, which is in terms of Chebyshev polynomials, has some coefficients Ci that we can use in order to estimate the error of approximation. And this is before we compare the tensor to the actual function. So what we did is the following. For the Black-Scholes pricing function, we again considered a sequence of tensors, all of them Chebyshev, and at each of them, or for each of them, we computed this estimated error using these coefficients Ci, and also the error empirically, that is in a very fine grid of points on the domain, and comparing it directly to the function. And these are the results that we obtain. Again, x-axis, number of grid points. So as you go here, you change the tensor. Y-axis in log scale is the error of approximation. And you can see that the predicted error with the CIs goes hand in hand with the empirical error, which is a very good thing to have, because without having to compare it directly to the function, which involves evaluating the function many times, you already have a good estimate of what the error of approximation is going to be.
Something worth mentioning here is that when we talk about the error, we're talking about the maximum error of the function, not the average error.
Yes,
also
that's
very
a good point.
It is that we're talking about the error here. This formula, this algorithm, gives us the maximum error that the function is going to have in the interval of approximation, not the average. And that is very important, for example, when you want a model to be approved by a regulator, because you can actually prove that the error is going to be bounded.
In fact, let me just quickly go to the theorem, which is one of the main things that we use. This one here, this error here is with respect to the supremum norm, which is for compact domains, which we always work on, is the maximum error, basically. So always bear that in mind. Good. So the other property that I wanted to mention, apart from the error estimation, has to do with the derivatives of the Chebyshev tensor. So if we've got a function that we want to approximate, and let's assume that we've got a good proxy to it, whatever it is, it doesn't matter what it is. It doesn't necessarily follow that the derivative of that proxy is a good approximator to the derivative of the function. However, with Chebyshev tensors, that does hold. That is expressed here in this equation that says that the derivatives of f will be approximated, and in fact, the convergence is also going to be exponential by the derivatives of the corresponding interpolant. So that is very good news, right? Because you may not even have an expression for the derivative of f, but if you've got f and you approximate it with a tensor, with a Chebyshev tensor, then you can use the Chebyshev tensor, take the derivatives, and that's going to be a good proxy for the derivative of f. Now, the next question is, how can you obtain the derivative of these Chebyshev tensors? And again, things really simplify down because there's something called the Chebyshev matrix, denoted here by D. But what it does is, if you take the values of the function on the Chebyshev points and you multiply them as a vector by this matrix, then you obtain a vector of values, f prime call them, that will be the values that you're going to use for the derivative of the tensor. And in this way, you obtain the derivatives of the Chebyshev tensor. So it's a very simple operation, really fast. You can do it as many times as you want for any order of derivative. So that's another of the really good properties that Chebyshev tensors have. So up to now, we've covered already all the mathematical properties that are of interest or relevance to us. But of course, none of them would be useful unless we would be able to apply it to the functions that we're interested in, which are pricing functions, because ultimately the main problem is a pricing problem in risk calculations. The good thing is that the vast majority of pricing functions are piecewise analytic. So meaning that outside of isolated points, which could come in the form of barriers, strikes, or payment dates, you've got pieces of functions which have high degrees of smoothness for which all the results that I mentioned before apply. And so, at least on paper, it makes sense to consider these Chebyshev tensors as good approximators to these functions. And given what we said about the barycentric interpolation formula, well, given that it values really fast, it could be a good replacement for the pricing functions in the risk calculations that we're interested in. So before we jump to the next section, let me just quickly summarize what is it that we covered in this Chebyshev tensor section. The first of them is that we've got a really good accuracy coming from the exponential convergence in terms of the number of grid points, which is equivalent to the number of times that you have to evaluate the pricing function. So not many evaluations give you a tensor of high accuracy. Second, once you've got the tensor, you can straight away evaluate it using the barycentric interpolation formula, which is numerically stable, very fast. Third, using the information at the level of the tensor, you can apply the fast Fourier transform and use the coefficients that result from it to give yourself an idea of the error of approximation. Then, that this tensor can be differentiated really easily, and that derivative is a very good proxy to the derivative of the original function. All of this is valid in high dimensions, and the good thing is that pricing functions enjoy high degrees of smoothness, hence it makes sense to apply Chebyshev tensors to them. Of course, there's a vast literature on Chebyshev approximation theory. Remember, of course, this all started at the end of the 19th century. Throughout the 20th century, there was quite a lot of work on it, and but the applications, especially in finance, are a much more recent phenomenon. So of course, there's quite a few papers that we can share with you. If you're interested, please get in contact with us. Some of them you can see here on the slide. But yeah, any questions you may have about references and stuff, we're more than happy to try and help you find. Okay, now let's go to the next section. Now that we have the main properties of Chebyshev tensors established, the question is, how do we use them then in risk calculations? And for that, I'm going to start with a typical diagram of the flow of a risk calculation, a typical generic risk calculation. So we start with risk scenarios. As an example, let's say we've got 5,000 of them. Then we need to price them with a pricing engine. So you've got a portfolio with many, many trades. You take the pricing function of these trades, and then for its pricing engine, you price all these 5,000 scenarios. You end up with a distribution of 5,000 prices. And with the prices, you obtain risk metrics, be it CVA values, capital amounts, et cetera, et cetera. And it's this step going from the 5,000 scenarios to the price distribution that constitutes the bottleneck that we've been talking about, the pricing problem in risk calculations. Of course, if you had all the computational power of the world available to you, this is what we would use, right? Because the pricing routines are very accurate. The cost that comes with that is, or the negative side that comes with that is that they can be expensive to run. So how does this change when we incorporate or we want to use objects like Chebyshev tensors into this calculation? And you'll see that not much changes. So first of all, we start with the same 5,000 scenarios. Now, the next step is, given that we want to replace pricing functions with Chebyshev tensors, we need to build these Chebyshev tensors. First step is to define, of course, the grid of points. Now, this point is very important, and I'll go back to it later on. But let's assume for the time being that you've got 100 grid points for your mesh, your grid, for the Chebyshev tensor. Then what we need to do is evaluate with the pricing functions these grid points. So these grid points get sent to the pricing engine. You end up with a Chebyshev tensor that is ready with a barycentric interpolation formula to evaluate these 5,000 scenarios. And what you obtain is a distribution of prices with which you can then compute risk metrics the same as we did before. Now, there's two important aspects here to highlight. The first of them is where the computational gains come in. So as you remember in the top diagram, you were evaluating 5,000 scenarios with your pricing engine. Here, you're only evaluating 100 scenarios with your pricing engine. So you're saving, we're saving ourselves 4,900 evaluations with our pricing engine. The calculation on the 5,000 scenarios for the risk calculations will come from the barycentric interpolation formula once we build the tensors. But this is so fast that compared to the rest of the process is negligible. So essentially, computational gains come from all those number of evaluations that you would have called in the traditional method, but that you don't call this time, which in this case is about 4,900. The second is, if you build the Chebyshev tensors appropriately, the level of accuracy is such that the price distribution here at the bottom is going to essentially match the price distribution at the top, and hence the risk metrics as well. And you'll be able to use these risk metrics at the bottom as if they had come from your pricing engine, which is essentially what we want.
And again, that's a very important point, because we don't, with this type of method, given that we can control the maximum error, we can match the price distribution, which is really what we want to do at the end, not only in average, which is something that is easier to do, but also in the tails everywhere in the distribution.
Yes, it's a very good, very important point. So I said that we needed to come back to this point here, the first one. How do we obtain the grid? So this is an important point because it's related to something that is being mentioned in other talks, which is called the cursor dimensionality. And it basically says, when it comes to tensors, that as the dimension of the tensor increases, the number of points on the tensor grows exponentially. Now, why is that a problem? Well, pricing functions, which are the things that we want to apply these tensors to, are just high dimensional. That's how they come. For example, take a Bermudan swaption. Bermudan swaption takes two curves normally, two yield curves, let's say 25 points each. That's already 50 dimensions. And on top of that, you've got the implied volatilities, and they usually come in the hundreds. So you're talking about a pricing function, which is in the hundreds in terms of its dimensionality. Just to give you an example, an idea of what we're dealing with, a tensor of 100 dimensions with 2 points per dimension is already at 1.27 times 10 to the 30 grid points, which is astronomical. That's just impossible to manage. So the question, of course, is how do we sidestep this problem? We've got three techniques that we normally work with, depending on the problem, to tackle this issue. The first of them is called the composition technique that normally applies within Monte Carlo target simulations, such as XVA, when you want to compute risk profiles and so on. The second one is called the tensor extension algorithm, which is a combination of Chebyshev tensors and some machine learning-like techniques, optimization routines. We'll go into them in a bit of detail. Both these techniques cover roughly a range of dimensionality up to about 30, and we'll mention what that means. And the third of the techniques is called the sliding technique that we've normally applied in the past in market risk calculations such as IMA, FRTB, and we've been able to tackle dimensions of up to 1,000 in this case. But the two techniques that we're going to be focusing on, because those are the ones that we're going to be using for the results that we'll present, are the first two, the composition technique and the tensor extension algorithm.
just to clarify that, can you go?
Mhm.
Yeah, we say that these two techniques cover up to 30 dimensions, but before you mentioned that a Bermudian will have absorption will have, for example, in the hundreds of dimensions. Well, actually, also these two techniques apply to that, but here this up to 30 is because we can apply a pre-dimensionality reduction, which is what Marian is going to explain right now.
Exactly. So think of the composition technique as a way of taking advantage of conditions within the setup, and we'll see how that is, that allow you to reduce the dimensionality of the problem. And that's exactly what we're going to go into right now. So what is a composition technique? As I said, we normally apply it within Monte Carlo simulations, and it's the following. What do you have in a Monte Carlo simulation? Well, in a Monte Carlo simulation, you want to simulate about 1 million scenarios into the future of some market scenarios, right? And let's take just a simple example. Say that you're interested in evaluating a Bermudian swaption on those 1 million scenarios. The pricing function of the Bermudian swaption here is represented by P. The input to P are going to be, let's say, a yield curve, a spread curve, and volatility values, volatility surfaces. So N here, the dimension, is going to be in the hundreds, as we said before. Now, the key thing is, how are these market scenarios generated within a Monte Carlo simulation? Normally, you use risk factor diffusion models. And risk factor diffusion models have a characteristic, which is that they, first of all, generate what we call a model space. Take, for example, the Hull and White one-factor model. This model first generates what we call what is known as the short rate. And then the short rate will parameterize the whole yield curve, regardless of the number of points that it has. But it's parameterized just by one factor. And that parameterization, we've denoted here by G, is smooth. So if we take, in the case of the Bermudian swaption, the collection of all those risk factor diffusion models that will generate all the market scenarios for P, and we put them together, we can take the composition of G followed by P. And in this way, what we've done is obtain a function F that, instead of going from Rn, goes from Rk, where Rk is going to be the space of these model risk factors, the short rate, the Gaussian factors, the factors associated to the Saber model, whichever model is it that you're using. And the key thing to notice is that suddenly a problem that was in the hundreds, we've changed it using the conditions of the setup into a function that has low dimensionality. In a typical situation with a Bermudian swaption, you end up with K being 3, 4, 5, 6, something of that nature, which is much more manageable for a tensor than the hundreds of dimensions that we started off with. So this is the composition technique. We apply it anytime that we have the possibility, because it just really makes problems way simpler. And the second technique is the tensor extension algorithm. So Catherine Glau yesterday gave a really good talk where she actually went into quite a bit of detail regarding what she calls the completion algorithm. We call them tensor extension algorithms, sort of generically extending what a tensor is. We're going to describe the algorithm, but in a much more sort of general manner. Hopefully, her explanation along with our explanation combine well to give you a better idea of what's going on. Indeed, I found out about this collection of algorithms through a paper that she put up on arXiv in 2019 with her collaborators Daniel Kresner and Francesco Stati. And the main idea behind this algorithm is, as you would expect, the main problem that we have with tensors is that they suffer from the curse of dimensionality, which is, as you increase the dimension, the number of points explodes. What can you do when you go beyond dimension 5 or 6, which is roughly the limits of how much in practice you can manage with a tensor? So what these algorithms say is, okay, fine, you can't save all the grid with the associated values, just store a subgrid, right? So here we've got a tensor where we've randomly sampled a subgrid of the original tensor. And that is what you're going to be, that's the information, the starting information that you're going to be working with. In some cases, and this is quite remarkable, given that the dimension of the tensors can be in the 20s, let's say, evaluating already a subgrid of about 3,000 points corresponds to about 10 to the minus 14% of the original grid, which is nothing, right? So the levels of compression are humongous. Now, the second aspect to bear in mind about these algorithms is we're going to be restricting ourselves to particular kind of tensors. And these tensors are called TT tensors. Now, TT tensors are tensors that do not store the information of the tensor in the traditional way, in the sense of grid points and values on them. That, of course, we know it's impossible for high dimensions. What they do is they encode the information of the tensor through a collection of matrices in each dimension. Catherine Glau yesterday went into a bit more detail into what is the size of these matrices, how you use them, and so on. We're not going to go into those details. Just the important thing to bear in mind is that these tensors, in some respects, compress the information into just a collection of matrices. And of course, if the matrices are not that big, then you can work with tensors in 20-something dimensions and 30 dimensions in practice in a computer. And now, what do we do once we've restricted ourselves to the space of TT tensors? What we're going to do is we're going to be using gradient-based optimization routines, very similar to the ones that I use in order to train deep neural nets. And we're going to be navigating the space of TT tensors, which, by the way, is a Riemannian manifold. It's smooth. So, of course, gradient-based methods work well on it to explore it. And the idea, of course, is the typical situation where you consider a TT tensor and you see whether or not that TT tensor restricted to the information that you started off with, which is the subgrid, matches or does not match, or to what degree does it match the information that we have. Of course, we separate the information into, let's say, a training set and a testing set. The training set being kind of the guide in order to try and find these possible TT tensors. And then we compare the error on this training set and also on the testing set. We let the algorithm run. And at some point, if the error is small enough, we use that TT tensor, which we know we can work with, even if it's in 20-something dimensions, as a proxy to the original tensor that we wanted to build, which is impossible in the traditional sense.
And one key idea here is, before moving on, is that by doing this, we are going to convert the cross dimensionality that in tensors, in direct tensors, it is exponential, to a linear law. So something that used to grow exponentially, now it is linear. So it really becomes the scale of the problem goes to another level.
Yeah, it's good. It's a good comment. It's important to highlight. I didn't put it here, but that by using these TT tensors, one of the things that we are able to do, and it was mentioned, by the way, by Catherine Glau yesterday, you're able to reduce the cost of storing a tensor, its typical sort of exponential cost in terms of the dimension, to something which is linear. And that, of course, completely changes what you can do with these tensors. So, well, this, roughly speaking, as I said, it was going to be sort of very intuitive general description of what the tensor, what the algorithm consists of. Now we want to use both the tensor extension algorithm and the composition technique for the calculation of dynamic sensitivities. And of course, once you've got a sensitivity, you can compute things like initial margin. So we're going to compute dynamic initial margin. So what do we have here? Well, we've got a Monte Carlo simulation. So this is today, we've got risk factors being diffused with a risk factor diffusion model. This is very important. Remember, we're going to be using the composition technique. And of course, as you know, you've got time points in the future, and the intersection of each time point with a path is a scenario such as this one. And that's where we're interested in computing, in this case, the sensitivity of a trade with respect to a collection of risk factors. So what is it that we do? We're going to be using, as I said, Chebyshev tensors. And roughly speaking, just to give you an idea, let's say that we focus on this time slice here. We're going to consider the domain of approximation given by the simulation itself, sort of maximum value and minimum value. That's where you're interested in working. You come up with a grid of a grid that will be the set of points for the tensor distributed according to Chebyshev. Then at each of those points, you want to obtain the sensitivity using the sensitivity function from your pricing engine. And once you build the tensor, you can evaluate it on all the scenarios that you generated. That's roughly speaking the idea. Of course, in this case, we start with a sensitivity function denoted here by SI. Very similar to what I had on the slide for the composition technique. This function here that goes from Rn, the market space, so n can be very big, is a function that we can't build a tensor for. So we apply the composition technique with the parameterization that comes from the risk factor diffusion model. And as before, we end up with a function. We can think of it as a pricing function f but not in terms of the market space, but in terms of the model space. So what is it that we estimated or that we simulated? By the way, the results are on a paper that you can download from Arca. We recently uploaded it. So feel free to download it, read it, get in contact with us. Any comments, more than appreciated. So what is it that we were interested in doing? Of course, we're interested in using the techniques that I mentioned and compare them to the benchmark, which is using the pricing functions that you would normally have in a pricing engine. Of course, computing dynamic sensitivities is very expensive with pricing functions. If you've got 1 million scenarios in your Monte Carlo simulation, given that you've got tens of sensitivities at each of these scenarios, you end up with about tens of millions of calls to the pricing functions. Which were the trades that we selected? We selected a spread option that had a Monte Carlo type of pricing function. So what we have is a nested Monte Carlo type of simulation, which is very complicated, always a challenge, and also an FX swap that has an analytic pricer. As we mentioned before, the market space can be in the hundreds in terms of dimensionality. We used the risk factor diffusion models in order to reduce the dimensionality of a problem. The risk factor diffusion models had 1 and 2 factors, but we had a collection of them, especially because the FX swap has many yield curves that it depends on. And after the composition technique, we reduced the FX swap down to 9 dimensions and the spread option down to 6 dimensions. By the way, this was done for the spread option and the FX swap, but it can be applied equally to many other types of trades. And these are the results that we obtained for FX swap. So on the left-hand side, you see a distribution of errors. We gave 2 of them, 2 examples, but of course, you have a whole sort of Monte Carlo simulation, so there's a ton of them. This is with respect to the first swap rate of one of the yield curves, and this is with respect to the exchange rate. And as you can see, both of them have an error of less than 0.5%. Across the whole simulation, the maximum error for the sensitivities was less than 1.5%, and the average error was below 0.5%. So that's the accuracy side of things. And of course, you want to keep it high, because otherwise you won't get reliable metrics. On the other hand are the computational gains, because that's where you want to alleviate the computational burden. The benchmark came down to about 20,000 evaluations. This is per time slice. The tensor extension algorithm applied to the function that you obtain after the composition technique relied on sampling the grid on only 300 to 500 points. With that information, we let the algorithm run. It ran for less than a minute. In some cases, even in a few seconds, it already had a very good candidate, TT tensor candidate. And each of these TT tensors evaluates the whole time points in about 15 seconds. So once you add up all the contributions from the brute force approach and all the contributions from the Chebyshev approach, you end up with computational savings of about 97%. Of course, with dynamic sensitivities, you can then compute profiles of initial margin. And the profiles came up to this. I mean, on the plot, you can't even distinguish the brute force from the Chebyshev. They're literally on top of one another. The one above corresponds to the 95th quantile of the IM distribution. This corresponds to the expected value. And the error at the level of expected value was 0.34%. This is the maximum error. And the maximum error for the 95th percentile was 0.32%. So very good results. Now, what happened with, or what can we see in the case of the spread option? Remember that what we had was a pricing function that relied on Monte Carlo simulation. So it comes with noise inbuilt into it. And the level of noise that we measured was about 8–9% for the 95th quantile of this noise distribution. So we don't really expect the tensors to do better than that or much better than that. What we normally notice in these kind of situations is that as you increase the number of points on the tensor, you quickly get to that level of noise, but after that, you won't really improve things any further, which makes sense because there's already an inbuilt noise in the tensor. With respect to one of the spots, because it's a spread option, so you've got 2, with respect to one of the spots, this is the error distribution for the sensitivities. So all of it roughly lying below 7.5%. most of it accumulated below 2.5%, which is pretty good. The maximum error across all the sensitivities computed was about 10%. The average error of about 3%. So the noise that we obtained in approximation is roughly within what we were expecting, given what we started off with. And what about the computational gains? Well, the benchmark in this particular case consisted of 110,000 evaluations. The grid was sampled on 12,000. It took about 2 to 3 minutes to train the TT tensor. Each TT tensor ran in about 11 seconds. Once you add up everything, you end up with about 90% in computational gain, which is pretty good. Again, the profiles, not bad, expected at 8%, 95th quantile at 3%, right? And as I said, we just put up this the paper with these results on arXiv. Please feel free to go download it and take a look at it. So right now, what we presented is within a Monte Carlo simulation, the calculation of dynamic sensitivities using composition technique and tensor extension algorithm. Of course, this technique is not limited to the 2 traits that we mentioned, nor to the fact that we're computing dynamic sensitivities. That can also be applied to pricing functions. So just very quickly, let me point out some of the things that we've obtained when we apply these techniques to pricing functions, given that with prices or distributions of prices in a Monte Carlo simulation, there's a ton of metrics that you can compute. This applies to XVA pricing, to IMM capital, to PFE profiles, and so on. Normally, we see roughly the same kind of results as we showed you for the dynamic sensitivity, so about 95% computational savings with errors less than 1%. Of course, if you're dealing with Monte Carlo type prices, it depends on the noise of the pricer. But a typical sort of profile that you would see is like the one that you see on the right-hand side, where the Chebyshev matches the brute force really, really well. And in this particular example, we've got errors way below 1% all across the board and really good computational gains. And just very quickly mention that these Chebyshev techniques can also be applied in a slightly different way in a different type of risk calculation exercise. In particular, in market risk, FRTB IMA, where you need to compute a lot of expected shortfalls, we were able to use Chebyshev tensors within the systems of the tier 1 banks. So this is really good because it means we were able to actually put it into the systems using real portfolios, applying some dimensionality reduction techniques to reduce the big dimensionality we're working with. And we were able to obtain really good computational gains of about 90%, errors less than 3%. Really good results that we were able to put together in a paper that you can, of course, get from arXiv, and that will soon appear in Wilmot magazine at some point next year. This will be, of course, sort of the most recent version. So stay tuned for when it comes out. And yes, that's basically it. So just quickly recapping what we covered here, we see that very good mathematical properties that Chebyshev tensors have make it very applicable in combination with machine learning type techniques in the estimation or the simulation of sensitivities or dynamic prices within Monte Carlo simulations for a range of traits. And the good thing is, but this is paramount, otherwise why wouldn't anyone use any of these kind of techniques, is that if built appropriately, really good levels of accuracy and also very high computational gains, which is exactly what we're after, because we're trying to tackle the problem, the pricing problem in risk calculations.
One thing I would add to this, which is we are computing the computational gain here. We are estimating it in the worst case scenario, which is the scenario in which we want to calibrate the Chebyshev tensors per run. However, something that you can do is once you create your Chebyshev tensor, you can serialize it, you can basically save it, and then you can use it lots and lots of times. So really, the computational gain is 93% in the worst case, but in practice, it can get well into the 99%
it can be high, yeah.
plus. Exactly.
Yeah, it really depends. You can start playing around with these things. You can start introducing into as a variable for the tensor, could be the strike, maybe even the parameters which underline the pricing model. So you can start doing a lot of stuff. And of course, the dimension will increase, but you've got the tensor extension algorithm that you can play with. Yeah. yeah, so please get in touch with us. Let us know what the problems are that you're normally facing within your institution. We're here to help. And yeah, that's it. Thank you very much. Any questions?
We have already one question in the chat. It says, how do you deal with continuous discrete barriers? That is a very good question that we have to face a few times. And the good news is that basically the question can be rephrased into, how do we deal with discontinuities in the function when the function has jumps or has kinks, this type of things, right? Now, in finance, the good news is that when that happens, well, the bad news is that when that happens, the function is not analytic anymore. So the theory that we have explained at the beginning does not apply. However, the good news is that in finance, the discontinuity points can be of three types. It can be strikes, it can be barrier points, or if you use the time dimension as one of the variables that you are approximating in your tensor, payment dates. The good news is that we always know where those barriers, strikes, and payment dates are. So what we can do is we can split the problem into a number of subproblems in a way that is so that we convert the problem into piecewise problems, and we can build a spline of Chebyshev of piecewise Chebyshev approximators, and that will solve the problem very nicely. I don't know, Marianne, if there's anything else you want to add?
No, I think you explained it really well. The way that you normally deal with these difficult points, which could be points of inflection or it could be discontinuities. Yeah, but as I said at some point, the important thing is to split up the domain of the function so that you're left with bits of domain of the pricing function that do not have these points, because you want to take advantage of the theory. Yes.
Can you go to page 35, because there's a question about it.
Yep.
It says, is there some structure in the exchange rate sensitivity error on page 35? If so, what do you think it is?
So again, the question is there any, sorry?
Any structure in the sensitivity error? So is there any logic here? Is it random? Is there any logic?
For that one there, yeah. Well, the way that I thought about that one when it came up.
No, the one he's referring is the exchange rate, the one on the right, actually.
The exchange rate for these sort of.
Actually, when you showed that plot, I thought the same, because you have these gaps there that have. So I don't know if there is something special going on there.
I don't know, to be honest. I don't know.
Okay, so the answer to that question.
I mean, they're so regular. There must be something. But I don't know exactly what it is.
There must be something. Yeah.
Yeah.
So the answer to the question is good questions. We'll investigate.
But no, sorry. We'll think about that. Yeah.
Very good. Any other question? We have 1 more minute in case there is a quick question, maybe. Well, thank you very much. And yes, no, that was a thank you note. Thank you very much, everyone, for attending. And if you guys have any questions, any comments, if you go at the last page has our email address, but also if you go to the website mocaxintelligence.com, you can see you can contact us from there. And also, of course, if you like the YouTube channel we just created, please subscribe to it. Thank you very much.
Thank you.
Thank you, Ignacio, Mariano. Obviously, as ever, we can continue this in the forums on the online portal, and of course we encourage everybody to go over to Mocax's YouTube channel to subscribe and ring the bell on there. Right, so on to Andrew.